Alright, we have done 4.1, and those are the exponential functions here. So now we move to the logarithmic functions here. So the main thing we should notice is the logarithmic functions and the exponential functions do have a relationship. The relationship is that they are inverse functions of each other. So let's jump to this here. We're going to define it. We're going to start evaluating it. We'll draw some properties from it. Then we'll look at, of course, domain. We're going to graph them and then look at the natural function and some applications here. But let's go to the definition here. Definition: what is a logarithmic function? Notice the logarithmic function is defined by an exponential function. So if you go over here, you say y is equal to log base a of x. That is defined if and only if x is equal to a to the y. And so what I want you guys to notice here, in the exponential case, notice the a to the y is sort of stuck in the exponent here. Notice if you change forms, you get y is equal to log base a of x. So the y now is equal to, over here the x is equal to. And if we think back to, remember, inverse functions here, since this is the y in terms of x, and now this is the x in terms of y, these guys are called inverse functions of each other. They undo each other's work, as we'll see when we look at some number examples here. Alright, so let's go with some notation, I guess, first. Whenever we look at a log function, we say f of x is equal to log. Then, of course, you always need an a for the base. You need a base here. Then you also need the number that we're taking log of. So there has to always be a base and then the log afterwards here. So log base a of x. That's what we're looking for. Alright, some examples here. So we're going to learn how to take from one form and move it to the other to solve. Let's see what happens here. So I don't know why they have braces here, but anyways, we're going to look at this right here. So write each exponential function is in logarithmic form. So 4 to the third power is 64. We know that because 4 times 4 is 16 times another 4 is 64. But if we take this and change it into a logarithmic form, let's see what happens here. So the 4 to the third power is equal to 64. Now it changes to log, and then we go back to ourselves. Okay, what's the base here? The base is 4. So we've got log base 4 of 64 is equal to the 3. And notice logs are exponents. If you say log base 4 of 64, that number would actually be an exponent of 3. Alright, b here. So 1/2 to the fourth power is 1/16. Hopefully we can change it here. We write log. Think about the base. The base is 1/2 of what number? It's 1/16, and the answer is the exponent, which is 4. Alright, let's put some variables in here. A to the -2 is equal to 7. So if we do that, again, log of my base, so it would be log of a of my number, which is 7, is equal to the exponent of -2. So notice we don't really have to have numbers. We can actually just have variables in here as well. Alright, your turn. Can you do practice problem number 1? Alright, hopefully I gave you a little bit of time here. So here we go. So 2 to the 10th power is 1024. Changing it to log form because this is called exponential form. So we go log. My base is 2 of my number, 1024, is equal to 10. So just changing from one form to another. Let's go to the next one here. So 9 to the -1/2 exponent is equal to 1/3. So we go log of my base, which is 9, of my number, which is 1/3, and the exponent is -1/2. Alright, and how about the last one here? This one is just variables. That's it. P is equal to a to the q, which just means log of my base, which is a, of my number p is equal to q. And again, just so you realize that q, which was the exponent, now it really is what the log function is equal to. So we say log functions are actually exponents. They're the exponential value. I guess maybe better to say that. Alright, let's go backwards here. Let's go from logarithmic form back into exponential form. So log base 3 of the number 243 is equal to 5. And so what we do is we take this 3 here, we make it our base. The 5 becomes the exponent, and the 243 becomes what the number is equal to. And again, log base 2 of 5 is equal to x. Therefore, then the 5 is equal to the base of 2. X goes in the exponent. All variables here, log base a of n is equal to x. In this case, n, the number itself, is equal to the base of a to the exponent of x. Alright, of course, your job. Alright, changing forms here. So log base 2 of 64 is equal to 6. Now I do mine just a little bit different. What I do is I look for the base right away. Again, it's going to be the same thing that you did already here too. But I look for my base right away, which is 2. And then I look for my exponent, which is 6, and is equal to the number that was initially inside the log, now becomes on the outside equal to. Okay, part B was log base v of u is equal to w. Again, just all variables here. See if you can just move around variables without contemplating the numbers themselves. And I go, my base is v, my exponent is w, and the number inside the log was u. Now it's outside as a value. Alright, so let's take a look at log values then. Let's see what they actually look like here. And again, just real quick here from the textbook. If you say log base 5 of 25, what you're really saying is, what's the exponent do you put on a base of 5 to give you 25? That's exactly what you're saying here. So if you change it into exponential form, you say log base 5 of 25 is equal to y. And then we say, okay, well, the number is 25. Well, the base is 5, and the exponent's y. What number do that? I can make bases exactly the same, and if I can do that, then my exponents have to be the same, so y is equal to 2. Again, that's the way the book does it. I'm going to do it maybe just a little bit easier, just so we don't have to go through writing that problem down 3 times until we're done. So let's jump to this here. So what log base 3 of 9, and you should almost pretty much start to be able to do this in your head. So then let's log base 9 of 1/3. What's log base 1/2 of 32? Of course, they don't stay easy problems. They become a little more difficult and challenging. So let's go for it here. The easy one, though. In my mind, what I say this. What exponent do you put on 3 in order to give you 9? And if you said 2, you are done. If you did want to really change forms, you would say this. What exponent do you put on 3 in order to give you 9? And whatever's in that box has to be the true answer here. In this case, it's going to be 2. But of course, they don't stay simple. So now, how are we going to do this one? What what exponent do you put on 9 to give you a 1/3? Kind of gets a little bit more hectic here. So in this case, we should put our variable in here. So I got a base of 9. I don't know what the exponent is. I'm going to put a y for my variable is equal to what was inside the log itself was 1/3. Alright, now the name of the game really is get the bases to be exactly the same. So 9 to the y really is 3 squared, or 2 times y is 2y. In this case here, I'm going to leave that alone just for a little bit here. If everybody okay here. Alright, I do have some questions here, so let me just add a little bit more extra here. So what we really did is we did this here. 3 squared is 9 to the y. And remember how with exponents inside the function, exponents outside the function, what you do is you multiply them. So 2 times y is 2y. Alright, so 3 to the 2y is equal to, now let's work with this base here. 1/3 it really is 3 to the negative 1 power, because remember, an exponent of negative 1 really means reciprocal. Now that our base is the same, now we can really set 2y is equal to negative 1. Divide by 2, and how about y is equal to a negative 1/2? Alright, and then we go to, alright, just to sort of check it out here, let's see if that is true. 9 to the negative 1/2, is that really a 1/3? Let's see. So remember, with the negative and the exponent, that really means reciprocal. Or you could say that the square root of 9 is really 3. So if you take this guy's square root, that would become 3 to the negative 1. And if this makes sense, I think that does, right? Because remember, negative in the exponent really just becomes reciprocal. So 1/3 is equal to 1/3. That is true. Okay, how about this one here? Log base of 1/2 of 32. What is that going to be? Okay, like we said before, let's put the base together. Let's change forms here into exponential form. So 1/2 is my base. I don't know what the exponent is, so I'm going to put a y value there, but it's going to be equal to 32. Alright, I don't like the whole concept of a fraction here, so let me do this here. Instead of 1/2, I'm going to make it a 2, but if I make it a 2, I just took the reciprocal of it, so now I have a negative on my exponent, and how about just a negative y? Now I need to have bases exactly the same, so the 32, I believe, is a exponent of 2 here. 32 is really 2 to the 5th. Once my bases are the same, now I can just take a look at exponents themselves and divide through by negative 1. And how about if y is equal to negative 5? Alright, so there's my evaluation of logarithms. So we did the definition. They're just inverses of our exponential functions, and we calculated some things. So let's look at some basic properties. Take a look at these one at a time here. So if you want to have them right now, just to write them all down, there are 4 very basic properties that come straight from the definition. So the way we define logs, this has to be true. So log of a, or log base a of a, is equal to 1. Log base a of 1 is equal to 0. Log base a of a to the x power is going to be just x. And a to the exponent of log in the exponent of base a of x is just going to be x. Let's take a look at these individually. Let's put in some numbers here, see if it makes sense here. So for number 1, how about log of a base of 5 to the 5? So again, the whole question is this: what exponent do you put on 5 in order to give you 5? So if you translate it to exponential form, how about it looks like this? And of course, it's going to be just 1. That value has to be 1. So if you go like this, log base 7 of 7, 1. In fact, log base of any base, taking the number of any number, is going to always equal to 1. Okay, jump to this one here. Log base a of 1 is equal to 0. So we have log, let's stick with 5 here, 5 to the 1. So what exponent do you put on 5 to give you a 1? And it's going to be a 0 from algebra. So we would say 5 to the 0 power is 1. That is true. Alright, so my test here. Log base 3 of 1, it's going to be 0. Alright, a little bit more complicated, not by much here. So what happens here? Log base 5 of 5 to the 3rd power. What's going to be the answer? Well, we can actually evaluate this here. So 5 to the 3rd power. 5 times 5 is 25, times another 5 is a 125. But there's a weird thing that happens. If I just took powers of 5s, then I go, what exponent do you put on 5 to give you 125? That's going to be that same exact exponent. So really, this whole process, we could have just crossed off the log base 5 and the 5 and just gave this answer of 3 right away. Alright, maybe just another quick example here just to make sure we got it here. Go for it. So the answer right away should be 4, right? Because the log base of 7 and the number 7 itself canceled, and we're just left with that 4. And then, of course, the tricky one here, log base 3 of 3 to the 44th power. Whew, I don't think I want to evaluate that at all. But I know that log base 3 and the number 3 are going to cancel, so I'm left with just 44. Alright, and probably the weirdest one of the basic ones here. What happens if you have an exponent or a base and the log itself in the exponent? So let's do this here. Let's just for the numbers to work out, just to make sure we get confidence in our numbers here. What exponent do you put on 5 to give you 125? Again, 5 times 5 is 25, times another 5 is 125, so it's 3. So this whole entire exponent becomes 3. But then if you have the same base, you're going to take 5 to the third power again to give you 125. So notice the base of 5 and the log base 5 in the exponent will cancel each other out, giving you just 125. Alright, of course, have to do a second look here. So 7, a log base 7 of 343. And it's just going to be this number right here. If you want to evaluate it, 7 to what power gives you 343? And that is a 3. And 7 taken third power is 343. But really, we don't really need to do all that work because we can just say the base of 7 and the log base 7 in the exponent cancel each other out to give you 343. So how about this? 8 to the exponent of log base 8 of 29. Again, this base of 8 and this log base 8 in the exponent will cancel themselves out and give you 29. So those are the basic properties for logs here. Now let's move on to domain. Oh, sorry, we do have some questions just to test you on it here. So practice problem number 4. So here we go. Log base 5 of 1. What would the answer be there? Or what exponent do you put on 5 to give you a 1? That would be a 0. What exponent? Oh, no. Let's see. You got a base of 3, you got a number of 3, and 5 is in the exponent. And so, again, the log base 3 and 3 itself would cancel, leaving us with just 5. And this one here, again, the 7 as the base and log base 7 in the exponent will cancel themselves out just to give you a 5. Okay, now let's go to the domain. And so the domain of y is equal to log base a of x is going to be, it's kind of funny here, we'll take a look at it when we look at a graph here, but not including 0, it's anything above 0. That's the domain. So there's no such thing as log of a negative number, or log base a of any kind of negative number. How about the range? And again, the range is going to be from negative infinity to positive infinity. So again, logarithms of 0 and negative numbers are not defined. There's no such thing. So let's go on to some domain questions here. So if I see this here, f of x is equal to log base 3 of 2 minus x. This little piece right here has to be greater than 0. And so what we do is we just take this little piece in here, scoot the x over this way, and we say 2 is greater than x, or you can say x is less than 2. So the domain is from negative infinity to 2, again in parentheses, because we're not including that positive 2. So all yours for this one. Log base 10 of the square root of x minus 1 minus x. Alright, so we actually have two things here. Let's think about it here first of all. So we have the log, which is the square root of 1 minus x. So we have the square root function, that's a little problem, and we have the 1 minus x itself, that's a little problem. So let's think about this here. So for this to have a domain, we have the square root issue got to deal with here. So because of the square root, see if you guys agree here. Remember, numbers inside the square root could be 0 or positive. So 1 minus x is greater than or equal to 0 because of the square root issue. Now, because it's a log function issue, we have this one that we say that 1 minus the square root of x has to be greater than 0. So now my question is, what is more limiting? What is a more limiting agent here? 1 minus x greater than or equal to 0, or 1 minus x greater than 0? And of course, it's the second one. It's the second one because you can't include the 0 as well. So then we're going to take just the second one here. And we're going to, I'm going to subtract 1 from both sides. I'm going to divide through by negative 1, and I get myself x is less than 1. So again, as long as x is less than 1, I got myself a log function here. In this case, it's going to be from negative infinity to positive 1, again including those parentheses at the end. So there's the domain functions here. So I think now we're ready for the graphing. Let's jump to the graphing of these things, and we'll take a look at one particular one. Alright, whenever you're graphing these log functions, you really have two different methods here. First one, And if you don't know what a graph looks like, remember you can always, this is the default here, you can always just go back to what graphing points, and if as long as you can plug in some points and get the value of them, then you got yourself a graph here. So this is, again, this is the long way, but it works. So if you plug in any kind of x into this here, but of course it's not just any kind of x, you have to sort of think about here. Let's see what number I can plug into here so that when I take log base 2 of that number, I get myself a good answer. And so I'm going to plug in a 1 because I know that log base 2 of 1 is going to give me 0. Then what I'll do is I'll plug in a 2 because log base 2 of 2, what exponent do you put on 2 in order to give you a 2? 1. Then I'm going to plug in a 4 because log base 2 of 4 is equal to 2, and then I got an 8. Log base 2 of 8 is going to give me 3, so notice I got myself some values here. Now I can graph it here. Got my little graph paper here, got my 0, 1, 1, 2. I can even go negative if I like. I can go down this way. But I got myself that looks like this here. Again, 4, there's my 4 goes to 2. There's my 8 that goes a little bit above 3, but about good right there. So there's my graph. Alright, another way you can do it, and this comes off of the fact that these are just inverse functions here. But before we go on here, I guess a few things here first. Make sure you put arrows at both sides or both ends of this because it does keep on going down. It does keep on going higher to the right. Then also we've got to add one more little piece, which the book sometimes talks about, sometimes doesn't. I'm not sure why. But you have ourselves a vertical asymptote. It never is going to reach x equals 0. Remember that whole domain issue. There's never a time where you can take a log of a 0. Alright, because of that, we do have to put the vertical asymptotes here. Okay, now the other side here. What happens here? Since we know the exponential function is actually an inverse function, we're going to graph y is equal to 2 to the x. And then what we'll do, we're going to just switch the x's and the y's. And so we have ourselves x and y. That's easy. It's easy really to put these down here. So 2 to the negative 3 is going to be 1/8. 2 to the negative 2 is going to be ourselves a 1/4. 2 to the negative 1 makes 2 to the negative 1 is a reciprocal, so 1/2. 0 plugged into here gives you 2 to the 0 is 1. 1 plugged in gives you 2 to the 1 is a 2, and then 2 plugged in gives you 2 to the second is a 4. So again, if we can graph these points here, negative 3, 1/8, negative 2, 1/4, negative 1, 1/2, 0, 1, 1, 2, 2, 4. And then we're going to reverse these, and we're going to get ourselves the logarithmic function. So let's go for it here. So there's my, don't need to graph all of them. In fact, the important points are the negative 1, 1/2, the 0, 1, and the 1, 2. As long as you got these 3 points, these are called the key points of exponential as well as logarithmic equations here. So now what we're going to do is we're going to, we can actually even graph it if you like. There's my exponential function. And remember, exponential functions have horizontal asymptotes. So y equals 0 right here. So now let's reverse it. Let's switch the x's and the y here. So negative 1, 1/2 now becomes, let me do the other ones here first here. So 0, 1 becomes 1, 0. Let's see, 1, 2 now becomes 2, 1. And negative 1, 1/2 becomes 1/2 negative 1. So based upon those, can you graph the logarithmic equation? Yeah, you can. Remember, exponential functions had a horizontal asymptote, so vertical functions have to have a, horizontal asymptote, vertical exponential, logarithmic functions have to have a vertical asymptote. Okay, so yes, so logarithmic functions come in different pieces here. If a is positive or greater than 1, a has to be positive in order for this to work here. But if a is greater than 1, we have ourselves the graph that we just looked at before. If a is between 0 and 1, so it's basically a fraction here. What happens is the graph goes down. Again, still has a vertical asymptote at x equals 0, but it comes from the top and actually goes down. So we say this is a growth function here. It's going up. Again, this is more like a decay function going down slowly. Alright, so let's take a look at some properties here. Now that we know that exponential functions and logarithmic functions are inverses of each other, I guess we should think about the whole domain issue. So exponential functions on the left, logarithmic functions on the right. So domain. Remember, for exponential functions here, you can go from negative infinity to positive infinity. And notice what happens here. The domain and the range are switched between the exponential function and the logarithmic function. Which makes sense, right? Because exponential functions and logarithmic functions, because they're inverses, they really are just the switch of the x and the y. Alright, so exponential functions have a y-intercept of 1. Therefore, the logarithmic functions would have x-intercept at 1. As we talked about earlier here, exponential functions have a horizontal asymptote, logarithmic functions have a vertical asymptote. They are both 1 to 1. Again, that has to be the prerequisite in order for them to be inverse functions of each other. Alright, and then some increasing, decreasing things here. Increasing is a is greater than 1. That's what happens to exponential functions. It's all about this a here. If a is bigger than 1, it is forever increasing. If a is between 0 and 1, it is forever decreasing. And then similarly here, because this base really is this base down here, it's the same exact value there. Okay, with that, let's do just a little bit more graphing. But what we want to do is we want to be able to graph using transformations. We already graphed 2 to the, that's our log base 2. So think about what's going to happen here. So x minus 3. And then you have the negative on the outside in front. So now first thing is, what's this negative going to do? Remember, what happens if there's a multiplier of negative in front of your function? And so if that is the case, then I think we have something called a reflection about the x-axis. And then what's up with the x minus 3? Isn't this going to move it off to the right 3 units? Remember, it's always the exact opposite here. So this is a horizontal shift, and it's horizontal shift to the right 3 units. Okay, let's see if we can graph this here. Again, by transformations. We went from graphing individual points. Now we want to move on. I'm going to graduate to graphing by transformations here. So let's start off with the regular log base 2 of x. And this one you should probably already know. 1, 0, very important. 2, 1, very important. 4, 2, very important again. And these ones not so much here. And then the other one here is 1/2, -1. Actually, these 3 points here are called the critical points. I just put in 2 more points just to make sure you see the graph well. And so first things first is we have a reflection about the x-axis. So let's change color here. Let's go to blue. So 1/2 -1 becomes 1/2 +1. 1, 0 still stays. 2, 1 now becomes 2, -1. 4, 2 becomes 4, -2. And 8, 3 becomes 8, -3. There's my blue, which is the reflection about the x-axis. Then I also have a shift to the right by 3 units. So we're going to move this blue dot, and we're going to go say 1, 2, 3. So we've got to name this point. This is called 3.5, 1. 1, 0 gets moved 1, 2, 3. So it goes to 4, 0. 2, -1 then becomes 5, -1. 4, -2 becomes 7, -2. And this one's going to move off here. 8, negative 3 now becomes actually 11, negative 3. All right, this green, these green dots is going to form actually our logarithmic function. We're missing one little piece here. We're missing the fact that it is never, ever, ever going to touch x equals 3. Okay, now we have to be introduced to two different logs that are used quite often. So one is called the common log. So a logarithm with base 10 is called the common log. And just like square roots, remember whenever you have a square root, you really don't put a 2 as the index. And so same thing here. If you see a log function and there's no number here, we assume it's a base of 10. That's what this means. Y is equal to log of, there's no number there, just log of x. If and only if x is equal to 10 is my base. Alright, so let's review those properties that we had. See if this is true. Log of 10 is 1. Remember, because there's a little base of 10 over here. Log of 1 is 0. Log of 10 to the x is just x. And then you have a base of 10. Log inside the exponent of that base. We'll just cancel these two out and leave you with x. Alright, I thought this was pretty cool in the textbook here. It just takes way too long to actually do. So I'm going to skip that, but if you're interested in looking at example number 8, that's a pretty cool law that happens here in mathematics here. Alright, that's one, something called the common log. But we want to also do something called the natural log. And we use this quite a bit, especially in calculus. And just what it says, natural law, there is a way in which we look at nature, and nature sort of lends itself to this particular law. So what is the natural log? We call it ln. ln of x is defined to be the log with the base of e. Hey, we've seen that before. Remember that in 4.1? We've seen log base e. Or we've seen the e value, 2.71828, blah, blah, blah. Well, if we stick e as the x, as the base here, what we do is we say ln of x. Okay, now the question always comes up, Mr. H, how come it says natural log, but then the letters are reversed? The L is actually first, and then the N is afterwards here. So, alright, because when we sort of discovered this, it was the French mathematicians that discovered it, and of course, French people are always backwards. They say log of the natural. So log of the natural then became ln or ln. So you can say ln, you can say natural log. Alright, and again, the basic properties here, ln of e is going to be 1. ln of 1 is going to be 0. ln of e to the x is x because the log, ooh, I did that one wrong here. Should say ln. Hey, cross that out. Glad I caught that. Let's change it right now. This is ln e to the x is going to give us x. There you go. That's the true number 3. I got to stop doing these at 2 o'clock in the morning here. That's all it is. Okay, and then we've got a base of e, and the ln now is in the exponent, and those two will cancel each other out, give you just x. Alright, of course we have to do some practice problems with them here. Let's look at some example from the textbook first. If you see ln of e to the 4, again the ln and the e are going to cancel each other out, leave you just 4. Now whenever there's a fractions or something like that, you do have to simplify a little bit here. So ln of 1 over e to the 2.5 will bring that e up to the top, put a negative for the reciprocal, and then the ln and the e going to cancel. Sometimes in the textbook here, yes, you eventually have to use a calculator because you want to approximate answers here. So you guys try this here, use a calculator. Can you find the ln button on your calculator? Should be a capital N, a capital L, capital N usually. And depending what kind of calculator you have, if you have a TI, once you type in ln button, it's going to open up a parenthesis and you're going to type in 3, close it off, and press enter button. Okay, and then some of you guys may have calculators that use Polish notation. Polish notation just means it does not keep track of order of operations. So if you have a smaller version calculator, you can't write ln. What you do is you say this: you write the 3 first, then you press the ln button. It'll give you whatever you need, and hopefully it's going to be one of those two ways that you're going to get it here. So 1.0986123. This is what you should get. If you don't, come talk to me about it after class. Alright, so how about ln of 1 over e and then ln of 2? Try that. Give you a few seconds to start it, and then we'll look at it together. Alright, ln of 1 over e. Again, we've got to bring that e up to the top, and if that is the case, we've got ourselves a reciprocal in our hand, so e to the negative 1 this time. Ln and e are going to cancel each other out, so we're left with negative 1. Ln of 2, that one you do have to do by calculator. And because you're doing by calculator and you're approximating, you put these little squiggly equal signs, not a straight equal sign. And it should look like this on the TI-83 or TI-84. It should say ln of 2, and then you close off that parenthesis and put out a number here. I'm not sure in the homework how many decimal places they want, so I'm going to just fill in a few over there. All right. Now we move to some applications here. We're going to look at some business applications and then some physics applications. So let's go for it here. This is the example in the textbook here. It says, how long will it take to double your money if it earns 6.5%? I assume interest compounded continuously. And at what rate of return? I think we've done these in 4.1. So now that we learned this whole concept of the ln function, let's see if we can do this a little faster. So let's see, just a quick example here. So if you say if P is the original price, that means the A value is going to be 2 times P, because you're doubling your money. And the book, I guess, should you know what, let's take a look at the example. Let's take a look at this one right here. So practice problem number 10. Practice problem number 10. Let's go over. So how long will it take for you to triple your money if it earns 6.5% compounded continuously? That's my question here. And then at what rate of return compounded continuously would your money double in 5 years? Sorry. In 5 years. You know what? I don't think it's doubling. I think that's the example problem. I think it should be like this. It should be triple. At what rate of return compounded continuously would your money triple in 5 years? So what percent are you looking for tripling that money? Alright, let's go for it here. So practice problem number 10. We go to the formula for continuous compounding from the last test here. A is equal to P e to the RT. And we want to triple our money based upon A. So we're going to put 3 times P, because that will triple the money. And then we know the interest rate is 0.065, so we can put that into T. So now my question really is, I got to solve for T. Well, it's kind of weird because I have a P variable here and a P variable here, but that's easy to get rid of here. If you think about it, aren't you just going to divide both sides by P? Okay, now we're stuck, because now the T is actually stuck in the exponent. So here's what we're going to do. We're going to change forms. This is exponential form. We're going to go into logarithmic form. So I'm going to change to log, but what's my base? My base is e, right? Log base e. Hold on, log base e is really just ln. So this is just ln of 3 is equal to 0.065t. So this would be log base e, but again we use the ln as the notation for it. Hey, look at this, no more exponents to deal with here. We just got multiplication here that I can just divide both sides by 0.065, and I got myself an answer. So ln of 3 divided by 0.065 gives me 16.9. So how long is it going to take? It's going to take 16.9 years for my money to triple at 6.5%. All right, and a physics problem. How about this here? It's kind of fun just to use a humongous formula. Oh, we have one more problem to go here. Part B says I got to use this again, and I got to think about what would my interest rate have to be if I wanted my money to triple in just 5 years. Now let's go back here real quick. At 6.5%, we learned that it was 16.9 years. So we want this to move very, very quickly here. We want our money to triple in exactly 5 years. And what's the interest rate that should make that happen? Well, again, we're going to put in 3p for the a value. And then we're going to put in a 5 for the t value. And don't like r times 5, so it's going to be 5 times r instead. Cool. Divide both sides by p, and we're left with this. Again, we're going to change forms. We're going to go from exponential form into logarithmic form. So log of e, or ln, is equal to, of 3 is equal to the exponent, which is 5r. Divide both sides by 5, so how about ln of 3 divided by 5? Now when you have to do it on a calculator here at this point, you got ln of 3 divided by 5 is 0.219722. How about 21.97%? You can say 22% if you like at that point. Okay, and one more problem to go is Newton's law of cooling, which is kind of cool here. It's cool. Exponential form of Newton's law of cooling is this one. And again, if you start solving for really the negative tk, then it's this one right here. Kind of fun to put in numbers into like a weird form. I like it. Okay, we're going to go to actually something that happened a few years back. It was on the news. Eventually there's some controversy about it, but if you remember that far back, if you are old enough to remember, there was an incident where the local McDonald's franchise, a lady went through the drive-thru. I'll just plainly say it here. And she got her coffee and she went on the road. Well, just a few minutes down the road, she spilt her coffee on herself, and to the point that she got, I think it was like 2nd-degree burns. And so the question was she negligent in doing that while driving, or was the McDonald's franchise responsible for that? So it turned out it was really a matter of how hot the coffee was when it was served. And so yeah, the McDonald's franchise paid an exorbitant amount of money, which I think she has retired from everything in life, and she just lives off that income at this point. But let's talk about what this means here. Let's go back to Newton's law of cooling. It says this, is that whenever you have something, an object at a certain temperature, it's eventually going to get to the temperature of its surrounding. It eventually has to do that. It may take a longer time, but essentially that's what it means here. So there's a few things here. So T is the temperature of the object itself. So there's T here. What's the temperature of the object? T of S is the surrounding temperature, maybe room temperature or something else like that. T is the temperature right when we start, and T is again the surrounding temperature, maybe room temperature. again, and then t is in terms of time. K is the exponential constant, and again, that's going to be different for depending what the object is. If it's coffee, there's going to be an exponential constant for coffee. If it's ice cream, there's an exponential value for ice cream. So whatever the substance is, each one of them have an exponential constant here. So let's see where we're at here. Let me jump to... So local McDonald's franchise has discovered that when coffee is poured from a coffee maker whose contents is 180 degrees Fahrenheit into non-insulated pot, after 1 minute the coffee cools to 165 if the room temperature is 72. How long should the employees wait before pouring the coffee from this non-insulated pot into cups to deliver its customers 120 degrees, which is required by law? It has to be 120 degrees Fahrenheit when delivered to customers. So let's plug all these values in here. It's 180 degrees when it comes out. After a minute, we notice that it cools down to 165, and then we do have a room temperature of 72. So then we're going to figure out the time value so that when it gets to the customer, it's going to be 120 degrees Fahrenheit. All right, long problem, but let's see if we can keep up here. So T, or temperature in terms of time, is this formula here given by the other slide here. We're going to plug in whatever we need here. So T, I'm going to change it to T instead of T of T. Easier to think about. So temperature of the surrounding was 72. That was the room temperature. Coffee, when it was just poured out of the coffee maker, 180. Subtract 72. E to the negative K times T, because T is what we're trying to find in the first place here. Okay, so our first job really is to figure out what in the world is K. What's our exponential constant for coffee? Alright, but before we do that, let's simplify this just a little bit more. The 180 subtract 72, that could be simplified just down to 108, e to the negative kt. Okay, so we do one trial. We do that and we find out that in a minute, the coffee does cool down to 165. So let's plug it in. 165 is equal to 72 plus 108. E to the negative k times 1, and the 1 means the 1 minute. Now we have our values in terms of minutes. Okay, let's move some stuff around here. How about subtract 72 from both sides? When we do that, we get a 93. 108 e to the negative k. Divide both sides by 108. So how about 93 over 108? Here's our problem. We got a little k. Our variable is stuck in the exponent. So let's change forms here. So how about negative k is out of the exponent is equal to the ln of 93 over 108. Divide through by negative 1. So we have our k constant for coffee. It is negative ln of 93 over 108. Again, assuming how hot it comes out of the coffee maker and assuming room temperature. So our exponential constant for coffee is approximately 0.1495317. Okay, the more decimal place values, the better, because the more accurate your results are going to be later on. Okay, so now we got it. We got our k value. So here's what we're going to do. We're going to rewrite what we have on top right here. We're going to rewrite it knowing what our k value is. So let's go for it here. So t is equal to 72 plus 108. And of course, you don't have to use, let me go back real quick here just so we know what we're doing here. You don't have to use this one, the initial one. We made it, so we simplified it all the way to here. This was our simplified version. And that was okay, right? Because it's just simplified to this right here. So let's rewrite this one knowing what our k value is. And so let me just do it real quickly here. So 72 plus 108 e to the negative 0.14953117t. Okay, if we need to give the coffee to the customer at exactly 120-degree temperature, we're going to plug in the 120 for the t. And this time now we're solving for the time factor. Again, we plugged into temperature, but this is time over here. So yes, capital letters, lowercase letters do mean different things in mathematics. Okay, how about subtract 72 from both sides? Gives you 48. Hopefully you guys are done already. Let's see, dividing through by 108 gives you 48 divided by 108. E to the negative blah 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 that's there. Alright, and again have to change forms again. So now we're going to take this exponent here. Now it becomes just the number itself times t is equal to the ln of 48 over 108. And again, you could reduce that. That'll be easy. How about dividing both sides by 12? That'll give you 4 over 9. That works. And then dividing everything by that humongous multiplier to t. Okay, plug it into a calculator. We've got ln of 4 divided by 9 being divided by that humongous number. On the previous slide, let's see, I should have put it that it was a negative initially here because you had a negative in front of ln. Alright, about 5 minutes, five and a half minutes. So it should stay out before it is served to customers. Kind of interesting there. Well, let me repair something here. Over here, the ln of 93 over 108, there should have been a little negative right here, which I did not put in, but it should have been a negative value to begin with. Alright, and that wraps up 4.2.